Welcome to day 1.
This is just a slight introduction to assembler. So it's a symbolic programming language, but it lies closest to the machine language in form and content. So it also uses our symbolic programming language, right? So the syntax, it has its own syntax and it has its own language structure. Okay, but only difference is it is closely interacting with the machine language in form and content. So you will have a good understanding of the underlying machine. Whereas in COBOL and all, you'll be at a higher level. Okay. And second thing is, it is very useful when to control your program closely. So up to the byte and even the bit level. So while coding in COBOL, you won't be thinking about bytes and bits, right? So you'll be thinking at a very higher level. But in case of assembler, you need to think at that level. So how your code will be converted into the machine language, that relation always you will have in mind. Whereas in COBOL, you write the code, you won't worry about what is the code that will be generated, machine code or the object code. But in assembler, you will get a hold of what will be happening when you convert it into object code. That also you will keep in mind. So when you write your program efficiently, sometimes when you're in COBOL, you leave it to the compiler to generate the code. But that also you can control when you write your programs in assembler. And then mostly it is used to write subroutines for functions that are not provided by symbolic programming languages such as COBOL, Fortran or PLM. So one such example is the date routines. So in many of the shops, you will see the date routines kind of utilities written in assembler because they are going to run many times within a program. So when you code such a routines, you want to be in an optimized way so that the total runtime, right, it takes to execute those programs will be optimal and you won't be consuming much resources. Okay, so that is the overall high level listing for assembler. And second, you'll see, so as usual, like any other higher level program, the assembler program will consist of many statements. Okay. In general, one assembler language statement corresponds to one machine language instruction. So ultimately, all your high level statements will be converted into machine language object code. Okay. But in COBOL, one statement may be converted into many object level code. But in assembler, it is one machine language instruction will be generated from one statement. And for COBOL, you have a compiler. We call that program which converts it into machine language as compiler. Similarly, there is a assembler which converts your assembler programs into machine language. So in assembler language side, we don't use compiler. We call it as assembler. So that is another IBM program only, system program which does that job. So in each shop, you will have that assembler installed in your IBM machine. Normally you wouldn't have noticed, but it is always available for you. COBOL compiler, anyway, by default you will be using. Assembler is there, but only it will be useful when you are coding assembler programs. And one more very important distinction between assembler and COBOL is there is no separation between data and instructions. You can mix and match data and executable statements. So that is a very big difference, right? In COBOL, you have to segregate your data, you have to segregate your instructions, but in assembler, there is no need. Only thing is you have to bypass those data declarations and then your control should go to the executable instructions. So you have to make sure of that. Otherwise, you can mix both data and instructions. So this is a sample program, assembler program. So even just we have not gone into any of the assembler structure, right? So to give you a feel of the assembler, I have given a sample program. So what do you think is the executable statements and what do you think are the declarative statements, data declarations? A, B, ANS are data declarations and the first three statements are the executable statements. So it is very cryptic, right? It is not very intuitive unless you know the syntax. So this is how all your assembler programs will be. So it has a definite way to code the assembler programs, right? So in certain columns only you can code certain things. Okay, so that will all come later. Okay, but for now you can have a feel of the assembler program here. So what it does is it is declaring three variables and then it has three executable statements based on those variables. So in assembler, we don't call it as variables. We call it as symbols. Right? So they are called symbols. And A, B, and ANS are three of the symbols we have declared. All of them are full words. We'll come back to see what is a full word and all. And the first three statements execute the load instruction, add instruction, and a store instruction. So your statements will be very cryptic like this only. But as you go along, as you know the statement, the instruction, different kind of instruction, then you will be able to understand. So all of you understand this data representation, right? What is in decimal, what is in binary, what is in hexadecimal. All of you should have gone through this at some point of time. IBM, we have this hexadic format of data. So in hexadic format of data, each character is represented as 1 byte. Okay. So in that 1 byte, you can represent how many different kinds of data. So ASCII also uses that, but it only uses the first 7 bits. But in hexadic, it uses all the 8 bits of the byte. So what is the maximum? How many characters you can represent in 8 bits? 256 characters you can represent. Okay. So out of that, what is the useful characters that are represented, right? So that is coming in that hexadic chart. So if you see the hexadic chart, right, you can understand what are the characters that are being used within the hexadic thing. Okay. So each that out of the 256 characters, right, if you see, you have this hexadecimal digits representing that 4 bits. So each 4 bits is represented by this hexadecimal. Okay. So starting from 0000. So this bit is hexadecimal 0, which is equivalent to decimal 0. Okay. Like that, each byte is consist of 2 hexadecimal digits. Right. So these are the important characters that represented in hexadecimal. So for example, hexadecimal C1, that represents the character A. Hexadecimal C2 represents the character B. Like that, the number 1 is represented by hexadecimal F1. Number 9 is represented by F9. Blank is hexadecimal 40. And some other punctuation characters are represented by these setting. So the remaining combinations, right, that doesn't have any meaning. So only these are the valid hexadecimal combinations out of the 256 bytes. So out of the command, there are totally up to decimal 255 we can represent in that 1 byte. Okay, so these are the various combinations of that 1 byte, starting from 0000000, this binary zeros, right? And then the last character that can be represented is FF, that is 1111, binary 11. So if we see the hexadic, right? So what are the, so starting there is nothing which is represented in hexadic, okay? But ASCII starts little before, okay? And hexadic, it starts with the period, which is hexadecimal 4B. And then AND symbol is there, and then various other things are coming, punctuations are coming after that. And then you have the small letters, hexadecimal 812, 89. And then it is also not continuous, hexadecimal 91 to 99. And then hexadecimal 822, A9. Those are the small letters, and capital letters start from hexadecimal C1 to C9, D1 to D9, E2 to E9. Whereas in ASCII, it is in different representation, because ASCII doesn't use the first bit. Okay, mostly it will start from the second bit only. But hexadic uses both the first bit to the last 8 bits. It has valid combinations. So that is how the numbers and the digits are represented in hexadic, that is in IBM mainframes, and mostly you will be using the hexadecimal format of these characters also in your programs for some of the instructions to make it clear. So inside the instructions, if you don't see, if you want to code in binary, you have to prefix with a B. The data has to be prefixed with a B. If it is hexadecimal, it has to be prefixed with a X. But if you don't give anything, then it will be treated as a decimal. So now this should be becoming clear for you. So what are the, so these are basically the printable characters. All other combinations will not be printed. It will be printed as some junk. But these are essentially the printable characters in your assembler programs. Okay, so that is about data. We come to another important part of the assembler program, that is called registers. Okay, so you will be closely interacting with the registers in assembler, whereas you won't be worrying anything about registers in your high level languages, even though when they are converted to object code, that will be converted with the registers as operands in the code, but you won't be directly involved with the registers in COBOL. But in assembler, you are responsible to interact with the registers to make your work done. So that is another important difference between assembler and COBOL. So registers are storage areas inside the processor itself. So you are going to do work directly with the registers, where it is not possible in high level languages. So you asked, right, why we choose assembler to write some of the things. So here you control the registers also. That is another important reason. So what are the advantages of using a register? No need to retrieve data from main storage or memory, because it is inside your hardware itself, and it is a shared resource that allows intercommunication between programs. So it allows you to communicate between programs. So it is a mean of sharing resources between different programs. So if you have a main program, if you want to call on another program, so the registers take care of making that connection between your programs. What are the programmer accessible registers? That means there are other registers which are not accessible to the programmers. There are two types of registers. One is the general purpose register. Okay. So how many general purpose registers are available? 16 registers are available, and they are numbered from 0 to 15. It is not from 1 to 16. Okay, you have to remember that the registers are numbered from 0 to 15, and each register will hold 4 bytes of data. So that 4 bytes together is called one full word. So at any point of time, your registers can hold 4 bytes of data. And floating point registers, normally we don't worry about that, because normal application programming, we won't be using floating point registers. But it is knowledgeable to know that there are 4 floating point registers available, and they are numbered from 0 to 4 and 6. And then it holds 8 bytes of data. And there are other registers for processor use, like access register, that we are not concerned. Out of these 16 general purpose registers, registers 0, 1, 13, 14 and 15 are reserved for special purposes. We will come later what is the special purposes. So normally what is available for you to program are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. All these registers are available for you to program. Coming again and again to the registers, but the basic knowledge you need to have about these registers. And then we have another important area of the mainframe, that is PSW, program status code. So this is a special area of the processor. It is 8 bytes long, contains important information like condition code, flags, etc. And the important thing is last 4 bytes contain the address of the next instruction to be executed. So in assembler, right, everything revolves around addresses. So when it is executing, the addresses play an important part. So the PSW holds the next instruction to be executed, the address of the next instruction. So when it is executing a current instruction, it will be holding the next instruction to be executed. And it also contains a condition code. Suppose we are making a comparison, it will hold the result of the comparison. So that is the main function of the PSW. All of you might have heard this PSW, right, at some point of time. Okay, we will come to the format of the assembler statements. So the very first column you have to put your label or a symbol. And then column 10 you will normally put the operation, and 16 you will put the operands, and whatever you code after the operands are called the comments. You can put any comments. So this is standard columns, okay, but you don't need to follow that. You just have to leave a space between the label and the operation and the operand, and then the comment. So for example, you have init 1, LA, R5, 4, and the comment. So these are the different parts of your assembler statement. So here, init 1 is your label, LA is your operation, R5 and 4 are the operands, and rest are comments. Out of this label is optional. Either you can have label or don't have a label depending on the needs. But always you should have an operation and the operands. And comments also is optional. So what are the rules for choosing labels? The labels are also known as symbols. Maximum 8 characters. It can contain alphabets, digits, @ hash symbol, dollar symbol. First character should not be a digit, and our label should always begin in column 1. You should not leave any space. So this is the general format of a assembler statement. So operation is the most important thing here. Depending on the operation, your operand should be there. So if you choose the operation, the operand should be in a particular format. You cannot violate that rule. So in this, how many operands are there in this example? We have 2 operands because they are separated by a comma. If they related to COBOL, right? If you take a move statement, how many operands can be there? For example, you say move A to B. So there A and B are the operands. Similarly, here for this load address, so load address is the operation that is shortened as LA. For that the operands are registers. 2 registers are the operands, register 5 and register 4. So there you can say move A to B or move B to A, but you cannot have more than 2 operands, right? There. Can you say move A, B to C? You cannot, right? Similarly, here we cannot have a third operand. Once you have the operation, the operands are decided accordingly. So you cannot violate that syntax. So once you choose your operation, the operand should be in a certain format only. So in this statement, we are trying to initialize register 5. So that is the comment. So operation is one of the over 200 machine instruction mnemonics. So that LA is called as a mnemonic for that load address instruction. So I have put 200 machine instructions, but actually there are now the latest assembler has more than 1000 instructions. Out of that, we will be only using, most commonly used will be about 100 or 150 only. Out of that only our most of the statements will fall. And other operations are available, but normally we won't make use of that. That may be used in some system programs. And the operand can be a register or a memory location or a self-defining term or a literal. So we will come to each of the what it is. But one of the operands is a register that we have seen, right? General purpose register or a memory location that we'll see how to define a memory location. Literal and self-defining term we will see later. How to continue assembler statement? You have to place any character in column 72 of the line to be continued. Continue the statement from column 16 of the next line. And maximum 2 continuation lines for a statement. So there is an exception to this. There is something called a macro. There you can have many lines of statements that we'll see later. So whatever symbols we define in a normal assembler statement is called an ordinary symbol. Okay. So these are similar to the paragraph names and the variable names, right? So they are very similar to the COBOL. So don't go deep about this. So here, whatever symbol we are using is called an ordinary symbol. The variable and sequence symbols are used in macro language. So that we will see later. But in this, so these A, B, A, and S are called ordinary symbols. So most of your code will be using the ordinary symbols. So in this example, we have seen the operation, right? For example, this load instruction, it will always have a register as the first operand and the memory location A. A is a memory location we have defined. That will be the second operand. You cannot code load 2,2. The symbols represent the storage locations or values, and then it has to be defined only once in a source module. You cannot have duplicate symbols there. And then it is advantages are easier to change. So if you define a symbol, it is easier to change. And then when you assemble the program, it will be listed in the cross reference so that you can see where at all it is being used. For a particular symbol, right? You can see how many places it is used. And then it is easier to remember and code. It reduces the programming. So what does it mean? Even without a symbol, you can refer to some memory location. Okay? So it is easier to code a symbol. So there are ways to get a memory location other than using a symbol. Okay? So that is what it is implied here. So sequence, variable symbols, sequence symbols and all we will see later. Okay, they are used for macros. Macro is some kind of a subroutine kind of thing. Okay, which you will be used to generate assembler instructions. So most of the common utilities, right, that will be coded as macros. So you don't have to code yourself. So you can make use of the macro, which will generate the assembler statements. Instead of you coding the assembler statements, it will generate the statements for you. So you'll see it later. So we have something called length attributes for a symbol. Okay. So what is this? If you want to define two variables, right? A1 and B2. So DC is for define constant. That is how we define a variable in assembler. Okay. I think we are moving ahead of this. Okay, we'll come to this slide later. I think this is okay. Let us take this base register, okay, and then we'll come back to the other thing. So the code I have shown you, right? It has symbols and labels defined. So the assembler has to convert it into address, right? So that is where your base register is coming. What is called as a base register. For each program, you have to designate a base register, right? So that base register will make use of the location. So it will store the starting place of the code in that register, and then it will be useful for representing that memory in a format called base and displacement. So if you take this, so if you take this A, so when you compile into object code, assembler will have to convert it into a address in the object code. So what it will do, it will take a base register. So you will designate a program in the register as a base register, and then you load the address of that particular instruction, starting instruction there. So assembler will take that base register and then convert this operand, which is A, into the base register under displacement. That is, each of these instructions is taking bytes of object code. See, for example, this load instruction will take how many bytes of object code? It will take 4 bytes of object code. So each of these instructions take certain bytes of object code, right? Because each instruction is predefined. For example, load means it is going to take 4 bytes of object code. So starting from the program, each of these instruction is going to generate certain bytes of object code. So when it comes to this A, we have already accumulated so much of object code. So this A will be at a distance of about 100 bytes from the starting of the object code. So what assembler will do, it will take the base register which you designate in the program, and then it will put the displacement. Okay, it will designate the 12. For example, you designate 12 as a base register. It will take 12, it will substitute 12 here, and the displacement which is 100. So at runtime, it will automatically calculate that, and then it will be able to take this variable, the number in that address. So this is the theory part actually, right? So that's how assembler will consider to convert your object code. Okay, let us take a program, sample program. Okay, this is just a template. I will try to explain you this first and then. Okay, so the name of the program is given in this line. So the name of the program is template followed by the word csect. So that gives you the, that's a, what is csect is a common this thing which you have to use in the program. So this identifies your program. Okay, so these are the standard entry conventions for your any assembler program, and then this is the exit conventions. So in between you have the body of the program. So for any assembler program, you can take this entry convention and exit convention. Out of this, one of this thing is establishing the base register. So here we designate register 12 as the base register. So all your symbols will be resolved with respect to this base register, that is 12. So what does it mean is, you cannot use the register 12 in any of your statements inside your program, because the base register 12 is going to store your base address that cannot be disturbed throughout the program. So here you are defining a variable, right? Save. So it will calculate the displacement from this address, we are coding many statements, right? That will be converted into object code of certain bytes. So for example, 4 bytes, 4 bytes, like that. So when it reaches here, it will be about 100 bytes from the start of the program. So this save will be converted into in the object code as base address in register 12 and the displacement of 100. So both those things will be stored in the object code. So out of all the registers, you have to choose a base register for your program, and that cannot be used for other purposes. For example, you want to add two numbers, right? So you have to make use of a register only. So for that purpose, you cannot take this 12 because already you have taken that as a base register. Okay, as I said, so this is the standard. You can code a program in many ways, assembler programs, but all of them should have an entry and exit conventions. Unlike COBOL, right? You need to take care of some housekeeping. So at this point of time, the important thing you need to know in this housekeeping is the base register, establishing the base register. So this BALR and using these together establish the base register. Okay, and then end of the program you have to do some things, and then this will be the exit of the program. So in between, whatever you code will be the body of the program, and the data you can code after this thing. So these are the data you have coded for this program. Okay, so just give me a second, somebody is calling. Okay, so you need not worry about at this point of time. Only thing you have to know is the entry and exit conventions for an assembler program. It is like your COBOL, right? Where you give the program ID and all those sections and all. So like that, assembler has certain things you need to do to follow the standard procedures so that your programs will not be abandoning or making some problems. For that, you need to follow these conventions. And one of them is the establishing the base register that you can change according to your wish. If you want to use 12 as a base register, you can use this, or you can use 10, 11, 9, or whatever it is. But usually you will see this register 12 being used as the base register if the program is small. And then if it is more than big sizes, then you have to use multiple base registers. So what I am going to do is, I am going to just compile this, assemble this program and then try to run this. Okay. So how to assemble this program? So I need to make a JCL for this. Okay. So Yes, the keyboard is misbehaving. Shit.
And I'll be running, possessed by a lone low voodoo. Fired up like a wolf on a full moon. And we're stuck in a la la land. The tides will turn without us. And I'll be killing time like I might be a cartoon. Take it in real life like haiku. I know we got the good vibes when pieces fall right into place. Even if I lost all my money, the zero runs deep, honey. And I don't need to speak a single word, 'cause you got me holding, holding. Even if my jokes aren't funny, my tongue tied up on it. And I don't need to speak a single word, 'cause you got me holding, holding. 'Cause you got me holding, holding. Play me like a bass guitar, simmer down and mess me up, tripping like I'm Jimmy at Woodstock. Drive me around in your red Ford, shivers down my spinal cord. Oh, 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 oh. 'Cause you got me holding, holding. Even if I lost all my money, the zero runs deep, honey. And I don't need to speak a single word, 'cause you got me holding, holding. Even if my jokes aren't funny, my tongue tied up on it. And I don't need to speak a single word, 'cause you got me holding, holding. 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining?
Okay.
When you're with me, baby, you are getting everything. Now you're dealing in diamonds. Don't you see that I'm shining? 'Cause when you're with me, baby, you are getting everything. 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining? 'Cause when you're with me, baby, don't you see that I'm shining?
You have to allocate a load link to it.
Here we go again. Trying hard, but you wanna be my friend. Ain't no place to hide, ain't no one to run to. Here
So this is the assembly listing, right? So if you see in the left hand corner, this is how your object code is getting generated. Okay. So this save is a macro actually. So it is not an instruction, it is a macro. So it generates 2 instructions when it is assembled. So how do you identify the macro? You can see a plus symbol after the line number. Okay. So out of this macro that is generating these 2 assembler statements, you can identify with the use of this plus symbol. Okay. So similarly, you have another macro, right? This return is a macro, so that is generating these 3 assembler statements.
Okay.
So LM is the operation code. LM, LA, BR and all are the operation code, and these are the operands. Okay. By giving that one single macro and the parameters, we are able to generate this 3 statements. We have one more macro here, that is WTO. So this WTO is generating how many statements? All these statements. So I told you, right, each statement will generate an object code that can be seen in your assembled listing itself. See, for example, so this is the address I was telling, right? At the assembly time, it will have an address. At runtime, it will have these addresses converted into appropriate addresses based on the where the program is getting loaded. Okay. So this statement, when this is an instruction, right? So the instructions, assembler instructions, that is the directions to the assembler how to assemble the program. So those won't generate any object code. Okay. So this template is a directive. So still the address is 0. And then the save is a macro. So the address is 0. So the actual address starts from here, STM. So this STM instruction takes how many bytes? It takes 4 bytes here. This is the actual object code. 90EC D00C is the object code. That is the 4 bytes. So the next instruction is at address 4. Because this takes 0, 1, 2, 3. So the next available address is 4. So this BALR generates 2 bytes of object code. So 4 plus 2, 6 is the next address. And then this ST takes 4 bytes of object code. So 6, 7, 8, 9. So what is the next available address? It is A. So all these things are in hexadecimal. So like that it goes on. So these are the object code generated out of these instructions. We will see how each type of instructions generates this. So for example, this ST, right? It starts with the operation code 50. All the ST instructions, if you see, it will start with 501.
Okay.
And all the STM instruction will start with the object code 91, hex 90. So there are rules for converting. So these are fixed by assembler, right? And what is the base address? This 006 is the base address because we are loading that using this BLR. So this 12 will contain this base address at the assembly time. At runtime, it will contain the actual base address, depending on where it gets loaded into memory. Okay, I think let us stop at this point.
So what is inside?